Okay, so let us start the second module. This is real-time data pruning. So this problem actually, again, the genesis of the problem is quite interesting for me. Actually, I normally do not work on power systems, and I was invited in 2013 by some power systems colleagues that they were writing a proposal for smart grid, and I was invited to participate because they told they are talking about deploying some grid monitoring devices. You can call them real-time IoT. These are called phasor measurement units, and these phasor measurement units will be in a given grid. My task given to me at the proposal writing stage that I have to come up with what are the optimal positions where these IoT devices should be placed and what should be the network capability, network basically architecture and capacity design was my task actually. So we wrote proposal, and when at that time I took curiosity that let us first understand before I do the network design, I have to figure out what are the end devices. Right? Any intuitive anyone will ask that question. That this is my end device. This is I call IoT. I call real-time IoT. So these PMU and PMU are called phasor measurement units, and they are supposed to be deployed at different points in the power grid, and they will be collecting the grid health. Okay, like we are these health gadgets. They monitor our pulse rate, etc., and likewise. And then they are supposed to transmit these information to these something called PDC, power distribution controller, and they could be local PDCs and there could be remote PDC. Remote PDCs are the ones which are called cloud data servers actually. Local PDCs are supposed to collect the data, and then on real-time basis they are supposed to respond to the grid health, and so that the grid's hazardous condition can be tackled. So this problem is critical in the sense those you might be aware of certain grid failures. Have you heard of grid failures anywhere? No? So in 2006 there was a grid failure in New York, and that happened in the evening, and later on it came in newspaper that 6 hours later there was some failure in Los Angeles. Okay, and then people did some data analysis and they figured out that this data network failure or grid failure that happened in New York actually had the cascading effect that far away, which is 6 hours flight distance, and that some failure happened, and they were basically connected. Point is that this failure and that failure are connected somewhat, and that was in 2006 that I heard actually. In 2012 we had a failure in India. We had a northern grid power failure. 2 observations actually, so not necessarily in our case. The failure happened in a place called Kanpur, and people actually monitored this. In fact, we do not have these PMUs in the normal grid today. There are some SCADA systems, these supervisory control data acquisition systems. These SCADA systems data was captured later, and then they figured out that some part of the grid, quite possibly 200 kilometers away, that SCADA system captured certain irregularity, whereas the failure happened somewhere else which is 200-300 kilometers away. Okay, and that was a cascaded failure. Actually, grid failure, if some source is tripping, then it will have a cascading effect because the users are drawing power, and then some source has tripped because of these frequency fluctuation or certain parameters were not proper, and then other energy drawers are trying to draw energy, and then grid cannot maintain it, and then other parts also get stripped, and as a result cascading failure happens. So 2 points here. One is that how do I monitor this grid health and not only the location of the grid where the failure is happening. As I mentioned, this failure location and the measuring location may not be co-located. And second is that if I somehow measure the disturbance at a particular point, for example, in our case, this in Mandi, this SCADA system captured the data and failure happened in some place, Kanpur also. So how do I capture this data, and then how do I figure out that where the failure is going to happen? So I will come to that as we go further actually. So what we are interested in this case is that my task was given very simple, right? My task was given that where to deploy these PMUs. You see, I cannot do over deployment. It is costly. PMUs today cost, each of them cost about in Indian rupees, this is about 5 lakh. 5 lakh you can convert to what price?
5 lakh.
3 lakh, let's say 2 lakh in Taiwanese dollars, and 2 lakh is 2 into 10 raised to 5 Taiwanese dollar. So it is reasonably costly. So what that means is that I cannot over deploy, I cannot under deploy, because I need to capture the grid health actually. And second is that how do I design the capacity? So what should be the let's say if it is wireless or if it is optical, what is the capacity of network that I have to plan actually? So to do that, what I looked into, I tried to look into the PMU data. So first figure out, let me understand what is the PMU data that is supposed to generate, the SCADA system data or PMU data. So these data I was able to capture for northern grid in India, and then I wanted to study this thing. So okay, so these some grid modernization, so motivation is this actually. So we have these grids typically collect sample 25 samples per second for 50 Hz system or 30 samples per system for 60 Hz system. And it can be actually today's these such devices are capable of monitoring at up to even 400 Hz and correspondingly 662 so many. Okay, and what we did is that what is currently these PMUs are being manufactured, and then these PMU data are being collected, and because they are real-time devices, these samples are collected and instantaneously transmitted to the PDC. So going back to these things, this slide here. So this PMU to PDC distance could be maybe few tens of kilometers, and then PDC should act on certain instabilities possibly within 4-5 seconds. Today, this grid control is done most cases manually, at least in Indian context, and this is not purely automated. In fact, most cases is not purely automated. What is being studied or proposed is that if they are automated, then how does the PDC react on these some PMU data on real-time basis? So we are looking at individual PMU data, which is called a IoT device, let's say real-time IoT device, and these samples are being collected and transmitted almost instantaneously to the PDC. So today this is done by optical fiber cables, which is dedicated, and because of that, people are not, these power grid providers are not worried about the bandwidth required. They are saying this is time, what is that called, the very critical infrastructure monitoring data. So they are provided kind of a significantly high energy bandwidth resource, which is optical fiber cables actually. So what I looked at, because I was interested in this collecting these PMU data and transmitting to the PDC, local PDC wirelessly. How do I let us characterize the PMU data actually? Okay, so let's get through the motivations, and the other aspect to motivate why I got into the problem further is that in the literature, this PMU data capturing and then the data analysis at the PMU end has not been done where actually it was not done. So because of this redundancy is handled at the PDC end or at the cloud end, and they have done some compression capability and then for the storage purpose. What we were interested in is so I'll go to quickly. Maybe come back to that. Yeah. So this is how this PMU data is varying with time actually. So this is what we have shown is some kind of instability region actually. So this is the 60 Hz system. 60 Hz system data is this is the frequency parameter. It is supposed to operate at about 60 Hz, but it is changing sometimes changing with time. So we have captured potential instability region, and these blue lines are the actual data is the green ones. Blue is predicted and training, etc. We'll come to that later. Okay, so what I am saying is that this is how the PMU data is being collected. Okay, so going back to the yeah. So as I mentioned, so today the PMU data redundancy. So one thing that we again, if we remember this figure, I try to switch back and forth here. Yeah. So if we see here, this is actually expanded version of a potential instability region. Most of the time, this data is quite stable, very slowly varying, and this is some very maybe fraction of few seconds or so. There is some sudden instability that can happen actually. So what that means is that most of the time the data has tremendous amount of redundancy, and very infrequent occasions there are potential valuable data actually. So to deal with that, what has been considered in the literature here is that this compression using fuzzy transform. So these are some literature that we have, but these compressions are being done at the receiver end, at the cloud end, cloud storage end actually. So these are the two potential papers that we have. In fact, we started generating results somewhere in 2016-17. Okay, so now two things that came to our mind is that how do we need to characterize the PMU data, and what part of the PMU data is of interest. And so PMU collects many other parameters. Those who have done three-phase electrical circuits, any one of you? Okay. Three-phase electrical systems, power systems basically. So if we are talking about generalized power system, these are three-phase system. So for each phase you are collecting these current, voltage, and the frequency parameter, and the rate of change of frequency. This is another parameter called Rokoff, and likewise for three phases and some other health parameters. Total some 8 critical parameters and some other health parameters. Total 15 parameters they collected. So these 15 parameters are being collected continuously at that high sampling rate, and then they are transmitted over the channel and so on. And out of them, apparently this rate of change of frequency is the most critical parameter. Okay, this my power systems colleague alerted me or gave me knowledge that this it is not the frequency but the rate of change of frequency is the most critical parameter. So we, to start with our research, we started with the rate of change of frequency as the primary parameter. So all other samples we just kept aside for the time being, because I was new to the system, power system data, and then we wanted to do stochastic characterization of the data. Okay. So whether the data can be is stationary, that is the first question, and then if it is stationary, then I can how do I model that, and if it is not, then how do I deal with it actually. That was the basic question we were asking. So when we collected this and we see that this sample autocorrelation function, if the data is stationary, then what will happen is that these autocorrelation functions should decay fast enough and then it should saturate actually. So what is happening is the autocorrelation function is actually changing with time and is also very slowly varying. So these autocorrelation function reduced to some range here and then it crosses further down and then kind of oscillated. So it says that because this autocorrelation function is not stabilizing with lag value, lag values are the samples actually. So sample 0 and we are considering autocorrelation function with respect to other samples. So the theory says that if the autocorrelation function saturates within certain range, 95% confidence interval, then we define that this data is stationary. So one thing that we find out, the data is reasonably non-stationary. What that means is that my classical stochastic approach of modeling is not going to be working. And then can I predict the data? The other thing that we are looking at is that by observation on the data values, we figured out that this data looks to be having tremendous redundancy. And then the question is, can we predict the data? What kind of prediction algorithm we could go for? So we tried to use, I think we have some motivation somewhere. We tried to use this. So there are some papers which actually tried to model, reference 15 here. So these ARMA process was used for modeling, and we were not getting very reasonably accurate ARMA modeling, because ARMA, what order we should consider? ARMA is autoregressive moving average. So moving average is actually about non-stationarity, right? Average is changing with time. But what is the order? And there we could not define any fixed order which is actually stably characterizing the nature. So what we quickly figured out that this data, we cannot use the classical theories that we have, stochastic theories that we have at hand actually. So we went to use something called support vector machine. We use support vector machine. So the idea is now that I have a bunch of samples that are being collected and that are supposed to be transmitted instantaneously, sample by sample. And now if I look at this data at the source is my PMU or the real-time IoT device, and if I can somehow predict the one sample from the past history sufficiently within certain accuracy, then I say that this sample is redundant, I will not transmit. And then I will continue that using my support vector machine. Support vector machine is trained using my past data, and then as long as I am able to predict the next sample, then I will decide that this data is redundant, let me not transmit. And on the other end, the PDC end, we will run an inverse algorithm, what is running at the PMU, and then PDC end will actually interpolate those samples. Those samples which are not being transmitted will be interpolated by the PDC end. Okay. So this is the technique that we have taken actually. So we have a single variate data. Single variate data is temporal correlation is very heavy as we studied, and this temporal correlation we wanted to exploit, and we call support vector regression technique. We made use actually. Again, no theory that we have. Now our key aspect here is that non-stationarity is handled using continuous learning and adaptation technique and offline computation of some model parameters to keep the low runtime complexity. So the point is that going back to so this I have already explained that this is kind of non-stationary that led us to go into that. So support vector regression technique is, I will quickly go through here. So if I have some past few samples, so D is called the lag value. So from the past few samples, we have to choose optimal value of D. Can I predict this if I have IL sample? If I can predict IL sample, then I will say that IL sample is redundant, and else I will transmit it. Okay. So the question is, this is of course very different from the thing that we mentioned about sample values, these I minus 1, I minus 2, etc., these sample values have to be assigned certain weights. So this is this one. So FI hat has to be estimated from the past samples with certain weights assigned to them actually, and with certain what is that called, bias. B is the bias actually. So the again task is that, so this is my auto support vector machines task is to predict these FI hats, and machine will be training based on these WAIs and this B bias. And this is a known, there is a very known theory behind it, so I'm not going to go through this thing. So this is the, so L is the length of time sequence, meaning that for training the machine, what is the length required? What is that called? This is called not regression length. This is the training length actually. So training length required, and then FAIs are called the attribute vectors, and WAIs are the corresponding weights. And so we need to, this nonlinear mapping that is happening, and B is the offset value. So we need to find these values. This is done using some technique called the kernel function. These details I will skip through. So this is the FI hat is obtained by optimization problem such that WIs are flat and error between actual and predicted values does not exceed E. E is given to me, so I will decide what is the accuracy level, or rather system provider will tell me that your prediction capability should be this much accurate. So this is given to me. Using that, I need to have this FI hat. Okay, so so this reformulated optimization problem here, and so this is some slack variable introduced. This is a corresponding complementary slack variable introduced. And this FI hat is done using something called this radial basis kernel function with parameter gamma. And effectively what I require is that I need to going back to this. I need to find these WAIs and AIs and B. These values are required, and this is the support vector machines parameters that are to be learned from these for a given length of this training sequence. So what we are doing is so at the source end we are so one unique thing that I wanted to emphasize here is that this PMU is actually sampling at a high rate, and in today's all the samples are being transmitted because they are time critical, they are health critical. There is no question of pruning and etc. So what we are talking about is that we want to actually prune the content before actually dumping, because there are a lot of redundancy. Okay, that is one thing. The associated thing is that I have the raw samples with me, and that is how I am predicting FI hat. I am predicting FI hat, and I am comparing with FI. FI is with me, ith sample is with me, and I am also predicting using my previously trained machine. This is trained using those parameters, this AWAI, etc. And then if I am able to predict, that means I have the raw sample FI, and I am predicting FI hat, and if my predicted value is close to that FI, then I will declare this thing. So summary, key point to take away is that my raw samples are with me. As a result, that helps me to figure out my prediction quality. Okay? And so I am doing that. As long as my prediction quality is within the error tolerance, then I continue. If I figure out that this prediction quality is moving away from the error tolerance, then I immediately start retraining the system again, and at that time I will transmit everything, because I don't want to, because it is time critical. So raw samples are being collected, and most of the time I am dropping them, I am not transmitting them, and whenever I find that my prediction quality is getting poor, then I will start transmitting everything. In the meantime, in the background, I will do the training again, because system dynamics has changed, and I will once I am trained, I'll pass the training parameters to the other end also, because other end has to do interpolation. Here I am dropping those samples, other end will do the interpolation. So that is what. So what that means is that earlier I was transmitting kind of a stream of data. Now I am transmitting sometimes a batch of data. They are all, whenever my training quality, what is that called, your prediction quality is getting poor, I am transmitting everything, and most of the time I am not transmitting anything. The channel is now basically utilized in a very bursty manner and very, very infrequently. In fact, the results are very encouraging actually in this. Yeah, so this is what I was talking about. So I have this thing. So transmit samples to the PDC and cross-grid hacker parameters are starts from the input sample, define the SBR model. SBR model is support vector regression model, and then this thing one-step ahead prediction. So basically from the trained SVM, I am using these D lag values, and then I am predicting the next sample ahead, and then if the sample quality is within the error margin, then I drop the packet, and if not, then I am going to, okay, so if this is within the error margin, then I am continue to proceed. If not, I am going to retrain, okay, update that status to PDC, and then again it is retraining. So this is the retraining happening again. And this algorithm is happening on the other side for the reproduction of the content. This is the simple thing that we have been doing. And then to capture this accuracy, we have another benefit of this algorithm. We have certain parameters called bandwidth saving BWS, and it is a total data samples versus this thing, data samples not transmitted versus this length over which we are monitoring. Retraining count, how frequently I have to retrain, and the disturbance identification index, actually meaning that there are some disturbance, and how accurately we are able to predict those disturbances. Remember that because these very, very health critical task of the IoT device, this disturbance index measure has to be 1 or more than 1, meaning that I should rather over predict, but I should not under predict, because your predicted potential disturbance versus actual disturbance. Okay. So, and the prediction ratio and another measure, root mean square error. This is a user and measure. This is also we are capturing as an output. Right? So I quickly show some of the these things. So lag value chosen, meaning that how many samples I should take for predicting the next sample. This is showing that this lag value is not, if I choose this large number of samples to predict the next sample, that is not necessarily very good actually. So up to 1, 2, 3, up to 5 somewhere, this is giving us reasonably good mean cross-validation error and choosing larger. So this is kind of a deciding for us what is the lag value, D value. And other question that we are asking is that what is the optimal training length? See again when as I was mentioning that when I have to retrain the support vector machine, then how many samples I should collect for retraining? That also has some overhead, right? Because if I collect so many samples, that means those so many samples are also being transmitted. So smaller is a problem, very large is also a problem, and so on. So this is another thing of critical interest. So this kind of says that this is the optimum training length, 300 is giving reasonable. This is kind of an empirical database set. So error measure is 0 to error measure is getting reasonably saturated over here. And for what are these two cases? Length of training sequence, and this is measures. I think these two are for different environment. Here, this is the steady state and this is the disturbed state. So in the steady state, the optimum training length required to be is reasonably small, about 300, and when the system is a little bit caught up then the training length required is a little bit large, so about 1000 and so on. So we kind of varied that, and we tried many cases actually. Average training length we kind of 600, 700, 800, etc. Okay, so these are some of the results that we have here. These are showing that my actual data versus predicted data and how frequently I am retraining here. So I have retrained here, and these are the retraining instances. So optimum training length, optimum OTL prediction length versus number of samples. Okay, so I think primary takeaway that I will have here is that here I have trained once here, and during the disturbed period I am spending a lot of time in retraining here, because it is there is a retraining count is increasing here, and here much less retraining here. I have retraining here, and then subsequently much less. Okay. So in all cases we are seeing that these my predicted data and the actual data are following reasonably quite accurately, and quickly go through. So these results are very encouraging in the sense that there are two cases we considered, so disturbed case and perturbed case and unperturbed case. So bandwidth saving is above 90%. Retraining count, this is for a given error tolerance. I think we considered 0.1 also. I will come back to that later. And base prediction ratio, disturbance index. As I mentioned, we actually chose to be disturbance index more than 1 because we don't want to under predict. And RMSE is 4. So there are some more results with regard to this optimum training length versus maximum. So there are certain trade-offs we wanted to figure out, that should we go for true training length all the time, or maximum training length, or maximum OTL, and okay, I think these are seconds. Okay, so these are so I think here the takeaway that I would like to emphasize on is that this epsilon is the error tolerance. So if the error tolerance is reasonably loose, 0.1 Hz, accuracy is sufficient for me, my bandwidth saving is high, retraining count is less, disturbance index is also quite high. Actually 1 is required, and it is over predicting. That is still reasonable, and RMC is this thing. And as I have more and more accuracy requirement, so 0.0001 Hz, which is a very stringent requirement, then my bandwidth saving is still 33%, 34%, and retraining count has increased significantly, which is intuitive, because I am more frequently have to retrain, and the disturbance index is kept above 1, and the RMC is of course correspondingly reduced because my accuracy level maintained is very high here. Okay, so this is, and then we compared with respect to what is the bandwidth saving actually. So compared with respect to composite sampling. So one paper that we found out that was talking about data transmission in a compressed manner and the source. But first of all, these papers' approach is not practically acceptable in the context that they are about compressive sampling. Compressive sampling requires a batch of samples to be collected and then acted on, and to transmit in a compressed version. So, but we see that this is doing our approach has performed better quietly, bandwidth saving wise. Okay, in this case, runtime wise it is being something, and disturbance index wise, etc. Okay, I think I will not spend more time here. So this is one module that was okay. So this is one takeaway that, this is not a takeaway, but another aspect that we wanted to emphasize. Okay, so to summarize here, we have talked about what is that called single variate. We have a real, let's say, IoT device, which is real-time IoT device, and out of multiple parameters, we have considered one parameter of critical interest, which is rate of change of frequency, and we are compressing the content or pruning the content at the source optimally so that we save bandwidth at the transmission stage. And what we have assumed in this case is that the network is ideal, meaning that my source is having some data which is significantly redundant, so I have pruned the content significantly. We are able to save about 90% bandwidth, etc. Now remember that 10% of the content that I am now transmitting to the PDC, I am considering for our practice. This is theoretical work, right? We got the actual field data, and using the field data, we have applied our pruning technique, the support vector machine based, and we are considering that through the network, when it is transmitted to the PDC, network is ideal. That means there is no loss, there is no delay in the network. Okay, so now which is a problem actually? Problem because earlier I was transmitting 100%. 90% was redundant. Now if the network is erroneous, some packets are getting lost, etc., I have no problem because they have a lot of redundancy. Now I am transmitting only the useful content, only about 10%, 15% content I am transmitting, but this 10% content is now very critical because all the uncritical data I have thrown away and only critical data is being transmitted. Now, so I have to now account for the network. If I have to account for the network error, then I have to do something more on it actually. Okay, so in other words, the work that we have done, and we have published a transaction paper on that, this work is good from the application layer perspective. At the application layer, we figured out that the data has tremendous redundancy. We have on real-time basis, we are working, propose some content, what is that called, support vector machine-based approach, single variant, and we are able to show that we have this much of benefit. Considering that the network, subsequent network is ideal, there is no loss of data actually. So this is I have not prepared additional slides here. So we have actually considered that if the network has error, if the network is error prone, because for example if the network is wireless, then how do I deal with such a situation when I have some very time critical data to be transmitted, and how to protect them actually. So I have to put some redundancy. Now the question is whether to put the redundancy later at the physical layer, or should I rather inject the redundancy at the source? So this is actually a joint source and channel coding you can think of actually. So one way for us is that at the application layer, I have decided based on everything, considering that network is ideal, so I have proved sufficiently. And when the contents come at the physical layer is alerted that this data has to be protected sufficiently. I have to put the sufficient protection. Now when I am putting sufficient protection, I am putting now additional redundancy, right? Again, those who have done networks, you are aware that at the application layer you try to prune the content to throw away redundancy. At the physical layer you inject redundancy so that you protect the content. We are talking similarly actually, but from this our practical context. That is one. Now question is, how do I put redundancy? What is the optimal redundancy I need to inject? This is one part. The other part is, I wanted to maybe draw a little bit here. So remember that I had this situation. This is my timeline. Earlier I was transmitting all the content. These are like streaming data. Okay. Now what I am doing is I am transmitting this content back and rest nothing. And again I am possibly transmitting these again. These are the returning instance. Again I am transmitting something and transmitting something and so on. So this is what my current channel utilization. Earlier this was happening this way, now this way. So now question is that when I have started transmitting something like here, when I have started transmitting a batch of data, this is my training instance, at the SVM is being trained again. It has actually lost the memory of the channel. This could be on the order of few seconds or maybe even larger actually. So if I talk about wireless channel, this here what was the channel condition is not possibly very helpful here, because this gap between these two transmission instance batches is very large actually. So the question here is that what kind of proposition I should have so that I put sufficient redundancy here, or rather I quickly learn the channel and then put sufficient redundancy so that I do not overprotect. Overprotection is that I am losing my gain. So 95% bandwidth saving that I was achieving at the application layer, I will possibly waste all of them if I put unnecessary redundancy here, and so on. So this is where we have proposed three variants actually. We proposed, one is called the Markovian approach. Okay, is that so if I consider a channel, a simple model could be that channel is good and channel is bad. So at this instant, so this is happening. This is probability P, this is probability Q, this is 1 minus P, this is 1 minus Q, and so on. And this P and Q can be learned from the channel if the channel characteristics is given to me. For example, if it is Rayleigh, then there are theory behind it. From the Rayleigh channel, this P and Q can be actually extracted. This theory is existing. Okay. So using that, I can actually calculate probability that channel is good. So let's say what is it called, probability of good at n step ahead. In a slot. Okay. This can be calculated. So first of all, from this I can calculate so this I have this thing, probability good, probability good bad, and probability bad good, and probability bad. Okay. From there I can calculate probability good, I can calculate probability bad, and this is nothing but this is one step transition matrix, one step state transition matrix, right? This is if the channel is currently good, what is the probability next instant channel is good, which is 1 minus P. PGG is 1 minus P. PBB is 1 minus Q. So this is given to you already, and these are also connected with the Rayleigh channel. Rayleigh channel theory is available. Likewise for other channels also a complex theory can be extracted. So P and Q can be extracted. So from P and Q, one step transition matrix, transition probability matrix is already known to me, and from there, n step transition matrix is, if I consider channel is stationary, then this is going to be multiplied by n. If it is non-stationary, then if all these channel states are known, then this is actually product form. The product form becomes a power form when this is stationary. So from the previous history, if I see that I have left this much time correspondingly this many slots, I can do some prediction, and using that prediction I can do something. So we have tried that approach, this Markovian approach. You can look at the paper. The other approach we consider, this is not doing very good, but this is still doing something better than doing nothing actually. Other approach that we have tried is that let us transmit the first packet with the worst possible scenario with sufficient protection, and then look for feedback, and then so this is called so one is Markov model, and another is we call probing method, meaning that when I transmit, while I transmit with most redundancy, I probe or send also a probing packet and then collect the feedback, and then I figure out in the process the channel state, and then I correspondingly apply the appropriate appropriate override. And the third approach we consider a learning-based approach. This has its own trade-off based on the previous histories and so on. It has been shown to perform better than these two. Of course, it has a problem in this computation overhead is increasing in that case. So we did something here, but again there is a room to improve, because here we have kind of broken the problem into source coding and channel coding. So source we have done whatever independently, that pruning capability, and then this what is the channel redundancy we will add. We have applied these three methods and we figured out that something is can be optimized by learning-based technique. We were doing something well. So this is in the context of real-time IoT single variate. So we have reduced the generalized IoT data to a single variate data because that was of our immediate interest. So next model that we have here, I think I am running out of time now. Okay, so I have many more slides to go, but I'll give a, so here now the next extension that we have considered is that I have a scenario. As I mentioned, real PMUs are actually generating not single variate data but multiple parameters together actually. So one immediate question that we have in mind is that for a single variate whatever we are doing, so this redundancy, similar redundancy might exist for other parameters also. So how do I deal with it? So I have so this is my blue line, likewise this is another, and maybe the red and so on. So one possibility is that should I apply these multiple single variate or can I do something better? So this is one temporal data stream, and I figure out its redundancy and then figure out what is the prunability is possible, and likewise for the other, and what else could be done. That is one thing. This is from the single individual node perspective. So I have individual nodes which are not necessarily generating one parameter but multiple parameters. So how do I deal with multiple parameters and figure out optimum pruning of the entire set of content that are being transmitted on real-time basis. Okay, so this is actually extension of what we did actually. So what we did instead, instead of a single variate SVR, we considered a multivariate SVR, and the theory behind is similar. But before doing multivariate SVR directly, what we have done is, this theory is very similar to what we have presented. I am not going to go through here. So these are the set of parameters, let's say 6 parameters of interest, and we figured out who are the correlated ones among them and have a cluster of them. So we figure out, for example, these A1, A2 and A4 are somewhat correlated, and out of them looks like A2 is kind of a leader. Okay, this is influencing A1 and A4. Okay, so this is a cluster, and A6 is independent. This is somewhat not correlated with any, and A3 and A5 are also clustered, and out of them A5 is the leader actually. Okay, so what we're doing is this group of data. So this out of 6 parameters, this actually there are theory behind it. So if you do PCA, in fact in the next slide we'll talk about this principal component analysis. So you will be able to figure out the correlatedness actually, of course in a different dimension actually. So by doing that, if I figure out they are strongly correlated, and that what is the strength of the correlation, we can also predefine. Let's say 0.6 is my correlation above which I got strongly correlated, and then I see that out of these 3 parameters I need to only transmit one of them, because from that I can somehow sufficiently well predict this two, and likewise out of these 2 streams I will transmit only this one, and this can be predicted from here. So now out of these 6 streams, I am left with only 3 streams. And on these 3 streams, I am applying whatever we did actually. These single variate SVM equivalent multivariate SVM. So that way we have gained significant benefit in terms of, as you can see, I have reduced the number of streams to be transmitted anymore, and then out of them we are further applying these multivariate SVM and eventually. So instead of this epsilon as one single parameter which was a scalar value, now we have an epsilon tube. So around which I have to maintain the accuracy for each of them. Okay, so actually this realization came when we actually we actually tried to implement our the data pruning technique on the IoT devices. We bought a PMU and then we tried to capture the data from the PMU, and then we wanted to work on that data by employing, and then we figured out that there are multiple other parameters that was there in the table also, that data we collected earlier for our testing, but that is one step. Okay, so this actually dealt with the multivariate real-time IoT. Now I'll give a pause here. So are there any questions here so far? This is another direction in the direction of real-time IoT, but are there any questions so far?
So in terms of the energy saving perspective, design your new protocol, how about the energy consumption for the purpose of learning?
Yeah, it's a very valid question. Actually, this question we have faced multiple times. So, 2 things in this context, because this is a power grid monitoring. So, our purpose has been to reduce the bandwidth saving, and because it is grid connected, I have not bothered too much about the processing energy consumption. But this is a valid question. What we are doing, we are still actually working on this problem. I'll explain where we are currently. Because this power grid, our main focus is how to reduce the bandwidth consumption so that the network load can be reduced actually. And in the process, we are also reducing energy consumption quite to some extent, because remember earlier I was transmitting 100% data, now I am transmitting possibly 80% data after putting some more redundancy at the physical layer. So 80% data I am transmitting, that means my radio interface is now 80% idle compared to the previous situation. So I am saving a lot of energy at the radio level anyways. But I am doing some processing at the suboptical training continuously. Okay, training part. After training is done, the prediction part is very epsilon. It doesn't consume much actually. We are going to generate results on that. Okay, so that is the result. So energy consumption has not been critical aspect in this problem particularly, but it can be measured. And as we discussed smart IoT, we will show energy as much more critical parameter here. But energy is still being reduced from 2 aspects. A radio interface is reduced, and where to do the computation is the aspect that we are focusing actually. So just to give a glimpse, imagine that I have multiple PMUs. So these are the PMUs, and this is the PDC. So imagine that each PMU is doing its own training and learning, and then PDC is send the trained parameters. Versus if you invert the problem, it is like edge compute actually. So if I, instead of let's say n PMUs doing their own training, I could actually pass that load to the PDC, and the PDC could possibly do the job not necessarily for each of them individually. Maybe it will do the training, and that training might be valid for the other PMUs also. So where to do the computation and is a way to address the question of energy consumption. We are actually currently investigating on that, and with energy as the emphasis. We have been implementing using RPi, implemented already, and then we are developing our own boards. And that is where the question comes actually. I'll come back to that question more. Any other question? So to summarize here, what we have done so far is that we have talked about real-time IoT. We have talked about, this is I call backward compatible real-time IoT, because I have the IoT device which has the classical sampling approach. It is doing over-sampled Nyquist data, that is giving me actually over Nyquist data. And then we are doing our own pruning, and for that I have to create a small engine. That engine is sitting either at the PMU or at the PDC, that is another debate. And I am able to reduce the content actually. And then we have done at the single variate level, at the multivariate level, and we have also addressed to some extent the question of what to do with the channel uncertainty. So channel uncertainty question can be asked from multiple angles. In our case, because it is a real-time context, then I have to put the redundancy appropriately. If I am dealing with non-real-time data, as we will see in the next discussion, then my channel uncertainty can be handled a little bit differently. Okay, so we'll discuss later. Now, this discussion that I am going to have now is actually very interesting. I was starting with a problem that at some point a grid node monitored certain unhealthy parameters, but failure happened quite far away. There is a PMU there also. That PMU did not capture. Okay, this is very interesting actually. So it is like a heart failure, not necessarily is originated at the signature doesn't come necessarily at the heart. Okay, signature might be at the leg somewhere actually. So this is very interesting. So question is that and this problem actually has not been handled. The other problem that is of interest to me is if the disturbance is happening, let's say at SP4, and how does the disturbance percolate? You imagine, this can be imagined as a circuit, electrical circuit. Okay, power grid connectivity can be considered as an electrical circuit. So at some point, you have generated some, what is that called, burst of current. Let's say some short circuit happened. That burst, how will it flow? Okay, it is like a water flow. If you have a certain lot of water poured, then it will take a certain low resistance path. Not necessarily it will uniformly go all directions, right? So we need to identify that actually. So basically, what are the vulnerable directions in the power grid? So that I can protect those directions appropriately. So meaning that how the disturbance propagates. First of all, what is the connection between disturbance and the failure? And second is what is how the disturbance propagates. And third thing is that one PMU data. So one PMU data may not be sufficient to capture the grid health actually. So this PMU might capture certain parameters. This other PMU might capture possibly certain other. Like we do our health diagnosis actually. So only blood parameter is not sufficient. Possibly I have to do heart, I have to do echo, etc., and combinedly doctor gives something. This is very similar actually. So question is that combinedly, how do I deploy these PMUs optimally where these PMUs are interested in saving bandwidth, but at the same time they are now not necessarily behaving alone, isolatedly. So far my discussion was that one PMU has a lot of redundancy, I am pruning the content efficiently, etc. But I see that I need to consider not only PMU's perspective, the bandwidth from PMU to the PDC, but entire system's perspective. So we call system aware pruning. The pruning that different PMUs should do should be system aware. And second thing is, given that system aware pruning is of interest, how do I deploy these PMUs optimally? Okay, so these two are the context that we are talking about. This is quite deep. Actually, this power system is not my domain at all, but we have published a transitional power systems very recently in that domain. And there are a couple of other papers where we actually characterize how the disturbance propagation happens. Okay, it is quite interesting. Okay, so the other aspect aspect of interest is that we were looking at the literature, and fortunately I had a student who had a power background. So he could actually educate me what works in power system, actually, power systems background. So what we figured out is that the literature mostly, rather, they deal with consideration that the PMUs have, when I deploy a PMU, so let's say this is my, I've deployed a PMU, and this is one path, this is another path, maybe this is another path. So I have deployed a PMU, they implicitly assume that all these three paths, these are called buses. All these buses are monitored, which is not the case actually. So these PMUs have certain limited current channels. Actually, normally a PMU comes with a single current channel. What that means is that when I deploy a PMU, it will monitor only one bus at a time. If I have to monitor all the buses whenever I deploy, then I have to have these many current channels actually. So equivalently the cost will be also increased and so on. So our question is that if I have PMUs, practically PMU come with limited number of current channels, typically one current channel. If I have limited current channel PMUs, how do I deploy this PMU optimally so that I can prune which is system aware, and then we want to see the corresponding benefits, etc. So that is the summary. I think I will skip through. So the bus information that I have is that this AW, weighted grid incidence matrix. So at any particular point, the grid connectivity, like in circuit, you can imagine that these not all points are this. So we have to figure out what are the points where I have to deploy the PMU, and if I deploy a PMU, why should I not deploy another PMU? So depending on whether this bus is being monitored, and then so that PMU, the next location can be may not be required, etc. And so this is, if you look at here, so minimize the this is the PMU placement vector solution CP. So we are talking about the CP is the mean cost, and GU is the observability constant. So we have to ensure that the grid is observable, and we want to minimize the number of PMUs. So that this overall cost is minimized actually, and maximize this quantity. This is actually the average bandwidth saving matrix. In other words, we want to maximize that so that we can prune as much as possible. So these two are the constant, and given these observability, your grid connectivity index is given to us. These are the constants. Okay, so I have not gone into further details over here, so you can look at the paper. So this is the kind of a grid incidence matrix, and this is using that. This problem is relaxed further. These two problems is combined into one problem, and this is my final optimization problem given this grid incidence matrix that I have in hand. Okay. So I think there is nothing much to be talked about, and subsequently these support vector machine that we have to employ for multivariate and system aware is following similar approach. There is nothing much to be stated. This kind of summarizes how this thing is done. So support vector representation model is used, and there is model reconstruction error propagation to all nodes property of the system. So that is, this is actually captured. If I need to know the connectivity, network connectivity, and then if network connectivity is given to me, my objective is to figure out where to deploy the PMUs optimally, and my algorithm will tell what is the compressibility at different PMUs. And restrict the reconstruction error within certain bound, and model the importance of each node in the system, and penalize the error violation quality, etc. So this is straightforward. Okay, so And we are trying to actually implement this task in real PMU. Currently, this is ongoing work. Okay, so I think major takeaway that I would like to carry from here is that dynamic prediction for single variate, and then unlike fixed rate transmission between PMU and PDC, the proposed approach exploits correlatedness, temporal behavior of the power line frequency, and to eliminate the redundancy of the data, and it has been able to capture these disturbances sufficiently so that and with suitable choice of hyperparameters. Hyperparameters are the S-beam parameters. These complexity is kept to be low, and so on. I think there is nothing. And cross correlation for the multivariate system, and this is about the system aware tunability. Okay, so this is kind of closes our RT real-time IoT as an example, PMU as an example. This can be mapped to other contexts further.